Hi everyone, here is a short summary of what you need to review from your basic statistics class in high school or at the university. So let's see. So the concepts that we want. The first thing to understand is when we are presented with a problem is to see, ask the 5 W's and the 1 H. In other words, we want to know when we are presented with data to really understand what were the individuals who were measured, who were surveyed. It can be not only people, it can be animals, it could be bank accounts, countries, etc. And we will see examples throughout days of the year throughout our course, determining what is being measured. The when was the research conducted is important. The where was the research conducted. The why, what was the purpose of the investigation, and how the survey was conducted. Was there a control group? Or there was some randomization in the way treatments were allocated to the individuals in the study. Now, sample versus population. Our goal is to describe the population having a sample that hopefully the best we can hope is a representative sample from the population of interest. So this is data from Amazon. So as we can see, if this is put in a Excel spreadsheet, it will look like that, set with lines. Here we have order number, we have the name of the buyer, the state, country, price, area code, etc. So these are not all the same type of variable, and that's the first thing we are going to learn about. Categorical variables. Which are a variable that tells us what group or category an individual belongs to. Synonyms for that, nominal and qualitative. For example, gender, country of birth, area code, teaching method, diet type, etc. We will see plenty of examples. Quantitative variable, on the other hand, is a variable that contains measured numerical values with measurement units. Is very important. And for quantitative variable, its measurement units provide a meaning for the numbers. Even more important units such as yen, cubits, carat, etc. So we know how far apart two values are. So we need that. With a unit, the values of a measured variable have no meaning. It does little good to be promised a raise of 500 a year if you don't know whether it is you're paid in euros, dollar, pennies, yen, or any other currency. Identifier variable, a variable that is used to uniquely identify the individual. Login ID, customer number, transaction number, social security. All of these are identifier variable. Then variable, ordinal variables that report order without natural units. For example, we get this a lot. How much do you like this? How much you strongly agree, disagree? So there is an order. And there is a whole course on categorical data which talk about ordinal data. 3 rules of data analysis. I can stress more important how. We should always draw pictures of the data, a summary, so that we can look for hidden things or things that we cannot imagine. A display of your data will reveal things you are not likely to see in a table of numbers, and will help you think clearly about the patterns and relationship. After all, that's what we want to describe. Do I see any pattern? So make a picture, make a picture, make a picture. A picture is worth 1,000 words, as they say. Now, displaying a quantitative variable, very popular histogram. Remember, it's not the histogram, a histogram. We can draw for the same data set different histogram depending on how we pick the bin width of the bars that are represented there. So the horizontal axis shows the values of the variable in order. And this is what we call a histogram slices of that axis into equal width bins. And the bar shows the count or percentage if we have a relative frequency histogram for each bin. Gaps are meaningful. They show regions with no observation. We want to understand that. The size of the bin in a histogram can influence its looks. That's why we have to be very careful. And our interpretation of the distribution, how the data values are distributed. There is no correct bin size, although recommendation is to use from 5 to 20. There is stem and leaf plots. You will see them in our textbook. For small data sets, they were popular before you were born. Dot plots places the dot for each data value, and we can see a pattern, and that's what we're looking for. Once I have the data, I want to say something about that data. Density plots move the bins in a histogram to reduce the effect of choice. How much the bin heights are smooth is still a choice that affects the shape, but the change in shape is less severe than in a histogram. Think before you draw. Every histogram, stem and leaf, and dot plot tells a story, but you need to develop a vocabulary to help you explain it. Start by thinking about these three things. The shape that we see, this, where is the center of that graph that we are doing, and let's think about the spread of the data. If it's spread all over, if it's concentrated in some points. So to summarize the shape of the distribution in terms of this, how many modes it has, if it's meaningful. Some data sets have as many points as they are because all of them are different. Whether it's symmetric or skewed, or whether it has extraordinary cases or outliers. That's really important. We want to see that in either direction. Modes. Does the histogram have a single central home or several separated? These home are called modes. The mode is sometimes defined as the single value that appear most often, but sometimes there are too many modes. So no use is useless when we have too many modes. In fact, no modes because each data value is unique. For quantitative variables, the mode is more ambiguous, okay? It makes more sense to use the mode to refer to the peak of the histogram. Okay, so this is unimodal. It's a little bit, if I describe it, it's unimodal. The mode is around here. It's a little skewed left. Here, I have a bimodal distribution, right? One mode here, one mode here. This, and it reveals. This is multimodal. So many modes. Uniform distribution doesn't appear to have any mode. And look at the wording because that's how you will write. That doesn't appear to have any mode and which all of the bars are approximately the same height. It's called uniform. Is the histogram symmetric? Can you fold it along a vertical line and get a pretty just match pretty closely, or are more of the values on one side? Generally speaking, we prefer to work with symmetric distribution because they are easier to summarize, model, and discuss. That is a famous model that you are aware of, that very famous one. It's pretty clear whether the center of the, where in this case, when we have symmetric distribution, it's clear where the center of the distribution is symmetric. So let's look at example symmetry. The histogram for a symmetric distribution will look the same on the left and on the side. So here, if we fold here, it will look like that. Both sides will coincide. This is symmetric because I folded here, the two ends. It's bimodal though, right? This is not symmetric. This is a skew to the right. This is symmetric, as we will write. A symmetric histogram is not necessarily bell-shaped, as we see here. It's more like a U shape. A histogram is skewed left. So look where is the small values kind of that are not with the rest of the observation. This is a skewed left and this is a skewed to the right. That's the vocabulary that we need to learn. An outlier is a data value that is far above or far below the rest of the data values. So we will point them out. We don't discard outliers. We just try to explain them. An outlier is sometimes just an error in the data collection, or when whoever recorded the data made also an outlier. An outlier can also be the most important data value. We want to understand what happened. Income of a CEO, temperature of a person with high fever, elevation and death value. These can all have that. Now, describing center. Typical values that we will use, very important, the median and the mean. And you know, this one, the median comes from ordering the data and picking the value in the middle. And the mean is an average. We sum all the data values and divide by the total number. So the median, it assumes that you are, right, ordering the data and then get the one in the middle. It will depend whether you have an even number of observations or an odd number in which you have here how to get them, and software will get them. The sample average, we add all the data values and divide. So every data value gets in the calculation, right? Contributes. That's why if I have outliers, this is going to be affected in either direction, right? Because it's taken as is. The median is less influenced by skewness or outliers than the mean. This makes it a good choice for summarizing skewed distribution, such as income or company size, value of homes, etc. The mean pays attention to each value in the data, but this sensitivity means that outlier and skewed distribution can pull the mean of the sign. Investigate outliers, correct them, use them, or set them aside. Spread, are the data all near the center or are they spread out? Is the highest value much higher than the lowest value, etc. To describe the data, we must discuss both center and spread. So let's see what are the measures of spread. We know that for center, we have median and we have the mean. Let's see about spread. So we have the range, the IQR, the interquartile range. This is the most popular. And besides this, okay, the sample standard deviation. So the range is the max minus the mean. The range is not that useful. The range is sensitive to outliers, because if this is the outlier, of course, it's going to show bigger percentiles and quartiles. So here is, with a quantitative variable, we talk about the percentage of a fraction. So it's that value, that data value, such that below that data value, I have a certain percentile. So when kids are born, immediately the doctor keeps telling the parents, okay, the height of your child is in the 95th percentile, so there is this information here. The famous one, the 25th percentile, 25% of the data values are below it, and the Q3 is the corresponding to the 75th percentile. So this is the vocabulary that we want to use, and the IQR is a measure of spread, or is the range of the Q3 minus Q1. So the really extreme values in both ends are not influencing these measurements, which is good. So it's measurement that is not sensitive to outliers. Provide a reasonable summary of the spread. Hard to explain to the general audience. Okay, but I don't think the standard deviation is better. Okay, now for the standard deviation, we want to know, I have the center of the distribution, the average, let's say. Now I want to know, on average, the data value, how far away are they from that? On average, all data values, how far are they from the center? That's what we capture in the standard deviation, but we need to start. This is how far each data value is from the mean. Okay, so I'm going to square those deviations and then average them, and we divide by n minus 1 because we estimated y bar from the data, and that's why it has this. So then the standard deviation, because this measurement here, when we square the unit of measurement as well. And that's why for the standard deviation, we want to go back. I want to say the mean is 130 degrees Fahrenheit, and the standard deviation degrees Fahrenheit, not degrees Fahrenheit square, for instance. So that's why we have that. So when we want to, what do we want to tell about a quantitative variable, we always start making some graphs and discuss the shape to see, say, you have a unimodal, symmetric, and if there are any outliers, and then provide both median, in particular when you have skewed distributions, and the IQR. So these four should be there. And in particular, if you have skewed distribution, make sure we mention that and report the median. Fact number summary. This is very necessary, and we use this a lot because we will put them in a particular graph. Fact number summary, the median, the quartiles, and the minimum and maximum value. Is a good, it captures a good summary, concise summary of the data. And they are depicted in this graph, which is called the box plot. It's very useful, in particular when we are comparing data from several groups. So that's where we are going to put it. The central box shows the middle half of the data. The length of the box is equal to the IQR. Okay. The median is roughly centered, and the middle half of the data is roughly symmetric. So all of these things are important. Whisker shows skewness if they are not roughly of the same length. Possible outliers displayed individually, you will see in many graphs. So at least string values will be highlighted in the, no, not on in the graph. On box plot, most of our computers, the Whisker using this rule of thumb, 1.5. Q1 minus the 1.5 times IQR, and Q3 1.5. So these are putting the range where then after, if any observation is above or below this mark, then they will be highlighted, and then you investigate. You say, well, maybe we have an outlier here. Okay, so outliers are observation below here or above. The smaller than this value or the larger than that value computed from the data, and I have this department statistics boxes that look like that. So it's idea to use them. We will use them a lot in this class, so you will get used. Transformation. We will use a lot the log transformation. We transform the data because for different reasons, but in particular, when we transform the data tend to look more symmetric, unimodal, or when we transform data, then and we are studying association between the two variables, the graph, the scatter plot may look more straight. So we see C-score is the last thing here. C-score, we standardize. So I have an observation, I subtract the mean and I divide by the standard deviation. I am getting that observation standardized, and this tells me how far an observation is from the mean relative to the standard deviation, right, of that set of measurements. So it's very important to be able Z-score measures the distance of a value from the mean in standard deviation. The Z-score of 2 says that the data value is 2 standard deviation above the mean. It doesn't matter whether the original observation was measured in whatever units. So that's good. It's about 2 standard deviation above the mean. One below, for example, here, the Z-score is negative 1.6, it means that it's 1.6 standard deviation below the mean. And this is all for this video. Thank you for listening.